Hello and welcome. Thank you for joining us today by attending our latest offering in our webinar series, Why Should You Use V-Cone Flow Meter in the Gas Production Chain? Before we get started and I introduce our speaker for today, we'd like to invite you to take control of your audience console. Use the controls to minimize or maximize each box to personalize your webinar experience. To resize a box, drag the bottom right-hand corner. If you have a question, please click the Q&A icon or use the open Q&A box on the right-hand side of your console. Click Documents in the resource area to download them for future use. And now it is my pleasure to introduce our speaker for today, Mr. Sean Reyes. Sean, how are you today?
Hi, Lisa. Doing well. How about you?
I'm doing great. Thanks so much for being our speaker today.
My pleasure. So thank you all for joining us. As Lisa mentioned, my name is Sean Reyes. We also have our senior support engineer, Mike Dyer, on, and he will be answering any questions that may come up. So if you see a slide and a question pops up in your mind, feel free to submit it on the Q&A chat section, and he'll respond to you while the presentation is ongoing. So without further ado, we'll get started with the presentation. So why use a V-Cone flow meter in the gas production chain? So I worked on this presentation along with our oil and gas sale development manager, Jean-Maria Caratolo. He unfortunately wasn't able to join us today, but we'll be sending a follow-up email. In case you have any questions, you will have both my information and his information to reach out to us. And today's agenda, we'll go over a quick introduction on McCrometer and V-Cone basics. Then we will proceed to V-Cone applications, followed by a Q&A session and closing comments. So introduction, McCrometer has been around since 1955. The company started when twin brothers McCall and their brother-in-law Art Crom founded the McCall-Crom Engineering Company in Hemet, California. Since then, it evolved into McCrometer, and we still have our existing facility in Hemet, although it has expanded significantly since then as we've grown. And since 1996, McCrometer has been a subsidiary of Danaher Corporation. And one thing that plays a big role in our manufacturing process is Danaher's core values on continuous improvement. And that's something you'll see a little bit of on this presentation as we proceed. And V-Cone basics. So what is a V-Cone? V-Cone is an advanced differential pressure primary element flow meter, and it's used to measure natural gas, wet gas, steam, hydrocarbons, and liquids in general. It's based on Bernoulli's principle, and it's supplied with a spooled construction to be inserted in line with the piping. It's composed by a flanged spool piece where a cone is welded inside. So how does this V-Cone meter work? It's got two differential pressure taps, and one measures the high pressure, which is the gauge pressure of the line. And the cone, because it's welded in, it conditions the flow area in order to generate a differential pressure, which is measured out of the low pressure port. And this differential pressure is will be a direct measurement of the volumetric flow inside of the line. And proceeding to compression applications. The first compression application that we'd like to go over is compressor anti-surge metering. So when it comes to this application, a surge is when the amount of gas being compressed is insufficient for the speed of the compressor. This condition can have catastrophic effects on the machine, and it prompts compressor manufacturers to include an anti-surge valve. The anti-surge valve takes recycled gas from the discharge to the suction side so that we can avoid system failure. And an anti-surge control system controls the valve whenever a low flow is detected. Common flow media that we see in these types of applications include dry gases, hydrocarbon gases, and air. And the typical line sizes are anywhere from 4-inch to 40-inch. Pressure classes range from class 600 to class 1500. And there are safety instrumented system and safety integrity level requirements. What we usually see in terms of accuracy requirements are 0.5% to 1%, and it also requires mass flow measurement. So in these cases, you couple a RTD port with the VCone flow meter, and using an RTD and a multivariable transmitter, you're able to compensate for changing pressure and temperature to give you a mass flow measurement. Now, how does VCone work as a solution for these types of applications? It provides an extremely stable signal, which means no damping in the transmitter. Now, the reason we're able to get an extremely stable signal is because the cone acts as a flow conditioner and ends up conditioning the flow to give you a very stable signal out of the low pressure port. When you have that stable signal, as we mentioned, there's no damping in the transmitter, which ends up meaning a quicker response time. So when you have that quicker response time, the shutoff valve or the anti-surge valve can go into effect very quickly. The other advantages of a VCone in this type of application is that it has proven structural integrity because it's a welded-in cone, there are no moving parts, and it also provides the options for multiple tapping sets so that you can have extra sets for redundancy if the application requires this. The case for compressor anti-surge is the case for actually multiple sets of taps on these types of applications, as I mentioned, is so that you can have redundancy measurement. So some of the meters that we've manufactured in the past have included different types of pressure sets of pressure taps. As you see in these pictures, we've manufactured double pressure tap set where one set is measuring a DP cell for high range, one for the low range. Another option is a double pressure tap set where one measures the process control and one is for emergency shutdown. We've also manufactured 3 sets of taps for Logic 2003 with 3 DP cells all fully independent of each other. And no matter how many sets of taps there are, every set is calibrated individually so that you can have a coefficient of discharge that is independent of the other tap set so that you can have a transmitter on each set and have them be independent of each other. And here we've got a couple of pictures of a VCone that was built for a compressor anti-surge application. As you can see, this is a 56-inch VCone, and it was used by Woodside, and it was fully welded in. And one great advantage of the VCone is that it comes in a compact spool piece, and it's a very customizable product. So when you compare it to a Venturi, for example, and in this case being a 42-inch Venturi, it ends up being much shorter than the 42-inch Venturi, even though the line size is significantly larger. And as I mentioned, that meter that we showed in the previous slide, it was welded in place. This was used by Woodside on multiple LNG projects. This was used on the LNG Train 4 in 2003, Train 5 in 2005, and Woodside LNG Pluto in 2007. Next application we'll go over is carbon dioxide injection, a case study on supercritical CO2. So when it comes to CO2 or supercritical CO2, the application challenges that are presented are that it behaves like a gas with a density that's similar to a liquid. The pressure versus density curve is nonlinear. CO2 injection pressures are over 5,000 psi, so we're dealing with very high pressures, and there isn't a test facility in the world that's capable of achieving operational conditions for supercritical CO2. Now, the metering challenges are you're trying to measure the CO2 accurately and trying to be within plus or minus 2%. Operating temperatures are about 104F to 158F, and the pressure, as I mentioned, these are high pressure applications, anywhere around 4,000 psi to almost 8,000 psi. So in order to work on these types of applications, McCrometer worked with a third-party calibration facility in the UK named NEL. So the way we calibrate these types of meters with NEL is that NEL first calibrates the meter in water at high, medium, and low flow rates and determines the actual behavior of the V cone, which is the coefficient of discharge. Now, they're basically trying to imitate how CO2 would act, but by using water. And then they use computational flow dynamics to model the same flow rates and determine the simulated behavior of the V cone. So again, it's a new coefficient of discharge that they are getting. They compare the two coefficient of discharge to establish a baseline error, and then perform computational flow dynamics at the supercritical CO2 conditions and determine these coefficient of discharges again. And again, they compare the two between an as-built and between an as-calibrated and a simulated coefficient of discharge. And when it comes to CO2 injection, this is a specific application where we had our meters calibrated at NEL, and there was they found that the accuracy would be within plus or minus 2%. So to go into a little bit more specifics, NEL calibrated over 3 flow rates, and they were 7.8 kilogram per second, 2.2 kilogram per second, and 0.6 kilogram per second. Now, this Reynolds number range was anywhere from 900,000 to 12 million. The temperature was the process conditions of the flow rate, so 104F to 158F, and the pressure was also the same as the process conditions, about 4,000 to a little under 8,000 psi, and there were 12 total simulated test points. Now, using the V-cone algorithm and the gas expansion equation, we were able to measure supercritical CO2 within plus or minus 2%. And the client that used these meters has bought about 48 of them, and they are all 10,000 psi rated V-cones in the 8-inch line size, and they've all been currently in service, so have been currently in service for over 10 years. Next application that we'll go over is LNG metering. And as you can see, we've got a number of references in the LNG projects, whether it's in North America and the Gulf of Mexico region, or Africa, or Asia, or Australia. We've worked on plenty of LNG applications, and I'm sure you're able to recognize any of these names if you've worked with LNG. So when it comes to LNG, the primary obstacle is manufacturing. So LNG requires meters being in cryogenic service. Cryogenic service is any time when the application where the operating temperature is below negative 238F. And sometimes they're expanding these applications to up to negative 150F. So the concern that the operators face in these types of applications is that higher alloys with special testing needs are required for use because of the temperatures. And fabrication of the cryogenic equipment is much more complex, so we need to factor in engineering safety and fluid contaminant. And then energy efficiency requires a minimum footprint to minimize head loss. So when it comes to these types of applications, fabrication and welding in particular is very critical in cryogenic service. We've got a picture of a V-cone meter, a 14-inch that we manufactured for a cryogenic application. This had 100% manual TIG welds, and the welders were qualified to AS&E Section 9 and EN 15614. And as you mentioned, manufacturing for LNG applications is very stringent. So impact testing of all the welds intended for cryogenic service per B31.3 proves that ductility is at design temperature. So all of these cryogenic procedures, they're not accepted unless we've got a minimum of lateral expansion of 0.03 inch and impact toughness, which is 27 joules average, but 20 joules minimum. And we use that even though it exceeds the B31.3 construction code. And primarily it's using strict process controls so that we can ensure the operation and long lifespan of all of the products that we manufacture. And just to go into a little bit more on the manufacturing, when it comes to welding these types of meters, we ensure that we are maximizing the austenite / minimizing the ferrite in the weld so that we can help ensure the ductility at these negative temperatures. And we also use special low ferrite weld wire so that the weld can have a maximum of 8% ferrite. And then at the end, all of the cryogenic welds are checked with a Fisher ferrite scope. And continuing, McCrometer is always ensuring that the workshop is clean so that contamination of welds cannot occur. And we only use dedicated stainless steel brushes, grinders, and grinding wheels so that we can clean the welds and base materials and ensure there isn't any kind of contamination. And of course, we provide factory tours should any operators be interested in seeing this in person. Those are all available at our facility in Hemet, California. And a couple of meters that we've provided for these LNG applications. As you can see, a lot of the products, and this is a trend that you're going to see, we specialize really in custom engineered products. So in the drawing on the left, this was a 14-inch meter built for the Fujian LNG terminal. This was built with beveled ends, so it was welded in place, and it had rotated sets of taps. Now, we're able to do all of this, whether it's a rotated set of taps or tap bracing, because V-Cone is an engineered product, so we are building it to match whatever the client's specifications are. It's whatever the client's piping spec is, that ends up being our piping spec. And the other drawing is representative of an 8-inch V-Cone, which was also beveled in place for the Costa Azul LNG terminal. This meter, as you can see, also had a special set of taps, which goes back to saying it's a customizable product, and it also had a custom overall length so that the client can retrofit in the existing pipeline. And continuing on to our next application, which is separators and test separators. So when it comes to process separators, they're typically used when more than one well and field deliver a fluid to the platform at the same time. Now, the fluids that are brought to the surface will require separation, and it's important to continuously monitor the oil, condensate, water, and the gas that's being delivered to the platform from each well. Often there's multiple meters in a very small amount of real estate, with each measuring a different media of the separating fluid. And the challenges that this presents is that when you're producing oil or gas or both, the separator separates these three fluids. As the gas moves away from the separator, it's going to cool and drop below its dew point. And that way it will be turning into a liquid and will become wet and cause instruments to overread. Now, metering engineers, a lot of major oil companies, they treat this gas from the separators as a wet gas. We know that V-Cone has a proven performance in measuring wet gas, and it's also beneficial in these locations because space and weight are an issue, and V-Cone only requires 0 to 3 diameters of straight run upstream and 0 to 1 diameters of straight run downstream, proving to be an advantageous flow meter in these types of applications. And the other advantages of using a V-cone in a wet gas type of application is that it has minimal interaction with the pipe wall. So liquids and particulates, they accelerate past the metering edge, almost bouncing off the metering edge. So it does not require any kind of drain valves, and it does not have any buildup anywhere on the cone. Compare that to orifice plate technology, where liquids and particulates will build up behind the orifice plate because they're always trying to go into it. And the metering edge of the orifice plate will quickly wear due to the carryover, and there's also going to be the need for drain valves. Now, using a V-cone in an application like this, there is no need to check, maintain, or replace the cone compared to an orifice plate where all of this wear in the beta edge will cause the operators to continuously monitor the meter and continuously have to maintain or replace it. And some of the calibration facilities that we've worked with on wet gas applications are listed below. These are the ones that we worked with in order to come up with our V-cone wet gas correction equations, which we'll go over a little bit more in the next slide. So when it comes to metering wet gas, we are trying to avoid the overreading error that the liquid inside the gas would cause. So when it comes to measuring these kinds of applications accurately, it's a very tough task to do. Using a combination of the V-cone equations and the wet gas correction factor, we're able to calibrate V-cone meters in wet gas applications to plus or minus 2% to 4%. And this really depends on your Lockhart-Martinelli number and Froude number. So there are some applications where a wet gas correction will yield a plus or minus 2%, and there are some where it'll be plus or minus 4%, but that is really the lowest accuracy that we offer on a wet gas application. This is for any wet gases with an operating range of 90 to 100% gas volume fraction. And when it comes to design pressure, V-cone is can always work with high pressures because it's built of the same components as the client's pipeline. So it's able to withstand pressures up to 15,000 psi. When it comes to repeatability, the V-cone meter is able to deliver plus or minus 0.1% or better, and turn down that you can get on a standard V-cone meter is 10 to 1, and then on certain applications we're able to offer more turn down, sometimes being 50 to 1, sometimes being 100 to 1, depending on if there's enough differential pressure. And to go over a specific wet gas meter that was calibrated at NEL, which is a third-party facility in the UK. This was a 6-inch Schedule 80 meter in service for 870 psi. The gas flow was 13.91 kilogram per second, liquid flow of 8.1 kilogram per second. Gas density is 73.4 kilogram per meter cubed, and liquid density of 806.8 kilogram per meter cubed. There was a plus or minus 10% band of liquid flow uncertainty. Now, when we calibrated this against a Venturi meter in the same exact application, we found that the V-cone had a tolerance of plus or minus 0.29 kilogram per second, which is equivalent to about plus or minus 2.1%. And the Venturi meter had a tolerance of plus or minus 0.36 kilogram per second at the same flow rate, which meant an accuracy of plus or minus 2.6%. Now, a difference of 0.5% may not sound like a lot, but in this case, that was about 0.07 kilogram per second, or 6 metric tons of gas per day, end up being quite significant for the operator in this type of application. So any improvement on accuracy makes a huge difference when monitoring a wet gas flow meter. And the next application we'll go over is wellhead metering. Now in wellheads, they can be anything from viscous oil to a wet gas, and they're often combining liquid, gas, and oil phases, end up being a multi-phase application. There's also some wellheads where they are using water or gas injection, and many of the well fluids have corrosive components that require special treatment. And wells may feed a production header, and the reservoir fluids are directed to the process plant via Christmas tree, which is what you are seeing in the picture next to the text. And wellhead pressure is reduced using a severe service valve called a choke valve. So when it comes to this type of application, the well fluid that is a gas but contains liquid is referred to often as a wet gas, just like we discussed. And then the liquid in the gas could be water or oil or both. As we mentioned, this liquid will cause DP-type flow meters to overread. And the wetness in the gas is described by a dimensional constant, which is the Lockhart-Martinelli factor. And in general, a gas is wet up to a Lockhart-Martinelli factor of 0.3. So whenever a fluid exceeds a 0.5 XLM, it's considered multi-phase. Now, users want to know the oil component, so as that is the high value, and they want to know the water component because too much water could be an unproductive well. As we are able to assist in these type of applications, there's a few things that we may need up front, which is the liquid volume fraction, so that we can establish the wet gas performance, and it included in the wet gas flow meter by the V-cone wet gas correction equation. And in these types of applications, end users will end up having to use tracer dye injection or test separators in order to separate the fluid into separate phases. Now, how does V-cone work as a solution for a wellhead application? So it's got easier piping and equipment layout throughout installation flexibility, and reduced platform weight and reduced piping costs. This is because of V-cone's guaranteed performance with minimal straight run required, which is 0 to 3 diameters upstream and 0 to 1 diameters downstream. The corrected dry gas flow for a wet gas application is plus or minus 2%, and the dry gas accuracy ends up being plus or minus 0.5%. As we mentioned, on a wet gas application, it's very difficult to measure, and we're using a correction factor to account for the overreading error, which is why we're able to get within plus or minus 2% accuracy. When it's a dry gas or a single phase liquid, then we're able to deliver up to a plus or minus 0.5% accuracy. There is no glugging or damming in the V-cone, which leads to a long-term performance without maintenance and a 25-plus year life expectancy. We have plenty of meters that were built in the 80s and 90s. They've been in service for over 25 years, and they've maintained their accuracy. And it still produces good results as the fluid approaches multi-phase. So when it comes to multi-phase, which is above 0.5, that's when really it's no longer a wet gas, but the V-cone meter is able to measure accurately within 0.3 to 0.5 XLM, which is the wet gas phase. And you can add a head recovery DP transmitter to add functionality, and this alerts operators on possible water breakthrough or when the liquid volume fraction changes so that the test separator or tracer dye injection can be scheduled. Now, testing on demand rather than periodically is going to save the operators a lot of cost. If they have a proven meter with a stable signal that can alert them immediately whenever the LVF changes or whenever there's a water breakthrough, they can change their control. They can control their process then, rather than just always be testing periodically and continuously spending money on that. And in these types of applications, in wet gas applications, we've had over 18,000 V-cones installed, and they've been in all sorts of environments, whether it's topsides, onshore, and subsea. And that's it for the applications portion. We wanted to go over some of our continuous improvements on V-cone flow meters. So historically, as mentioned, McCrometer is a part of Danaher Corporation, and we value continuous improvement very highly. We have a large R&D team on site, and they're always looking at different ways on either improving our existing flow meters or offering new capabilities for them, or working on new meters for applications that may be difficult to measure. And because this is a customizable product. It's an engineered solution. McCrometer assists engineers by saving cost, by providing solutions that a lot of other manufacturers cannot do. Some of the designs that we offer that are really for very, very difficult applications include hard-facing meters, close-coupled valves, manifolds, and transmitters, diaphragm seal taps, integral RTD and thermal well, so that if you want to compensate for changing temperature, liquid volume fraction change detection, and the multiple sets of taps for safety instrumented systems and emergency shutdown. And one case study that I wanted to go over is the improvement on our large V-cone flow meters. So our R&D team conducted a recent review which looked at how a number of things impacted V-cone flow meters. So whether it's a static structural analysis at its steady state, reverse flow, sudden depressurization of the line, vibrational frequencies, which could be due to vortex shedding of the flow or plant operational equipment, thermal stress due to expansion, and fabrication and welding practices. So when going over this case study, the R&D team found that very few applications, less than 1%, would require additional or more robust support. But they took the opportunity to improve the V-cone design so that it can work for these applications that fall into that less than 1%. They uncovered some unique and application-specific variables which could impact performance on some large-size meters. And these are primarily reverse flow, sudden depressurization, and resonant vibrational frequencies. Now, based on these learnings, we standardized on a robust design for V-cone meters of sizes 18-inch and larger. So as you see in these two drawings, the original design was basically McCrometer's legacy design, where it had one pipe support and two plate gussets. The new design includes 3 pipe supports upstream and 3 pipe supports downstream of the meter, and ending up beefing up the meter and just making it able to withstand a little bit more stress and a little bit more vibration. So the summary on the new design is that this is for large meters, as we mentioned, 18-inch and larger. The round gussets, instead of plate gussets, provide additional support upstream and downstream of the cone. They eliminate unsupported cantilevered weight, and they target resonant frequencies over 150 hertz, and of course withstand higher flow velocities and vibrational loading. So if there's any additional stress because of this higher flow, we've got a beefier design that'll handle it a lot for a higher value, basically. And as mentioned, this was rolled out for all 18-inch meters and above as a standard. And finally, to go over just a quick summary of what we've learned, there are minimum installation requirements on V-cone flow meters. This is because the meter only requires 0 to 3 diameters of upstream straight run and 0 to 1 diameters of downstream straight run. It provides a very stable signal because the cone inside the meter acts as a flow conditioner. So when you have very turbulent flow coming upstream of the cone, it conditions it so that you get a very stable signal on the low pressure port, and your DP measurement ends up being all the more accurate. Now, low head loss is one thing that's very important to operators. As mentioned earlier, the V-cone is an engineered solution. There is no one-size-fits-all. We are building these meters specific to applications. So if an operator has a requirement to stay within a certain pressure for head loss, we can manufacture the cone inside of the meter to be smaller than the average size so that there could be very minimal head loss delivered in the application. And when it comes to long-term performance, as we mentioned, McCrometer V-cone meters have been in service for over 25 years in many applications, and they've maintained their accuracy throughout this very long period of time. So the V-cone meter is a great meter that you want to install and forget about and not have to deal with again, because it does not require any kind of maintenance or recalibration. There are no moving parts, so it makes the operator's job very easy. It's self-cleaning, which is, again, a factor of the cone inside of the pipe. That's by conditioning it, it's also kind of self-cleaning itself. and high accuracy because it's able to deliver plus or minus 0.5% on any single-phase fluid, so whether it's a dry gas or a liquid. And on wet gas meters, plus or minus 2% to 4% accuracy, also applying to supercritical CO2 applications where they're very difficult to measure. And as we mentioned, it's engineered to suit the application. If an operator requires very high DPs for a large turndown, then the cone inside of the meter can be manufactured to a very large size. And then if low head loss is a requirement, then the cone could be manufactured to a very small size in order to fit whatever the engineer's needs are. So thank you very much for listening and watching. That covers it for the presentation. I see we've got some Q&As, and we're happy to answer any more that you may have. So Mike and I are going to be on the line. And should you require any PDF of the presentation, please feel free to reach out and we'll send you a copy of it.
Wow, thank you, Sean. That was an amazing presentation. I actually did have a question for you while Mike's answering those behind the scenes. Thank you, Mike, for doing that. I wanted to ask the V-cone, pretty much it's kind of a built to suit, correct? So we have a lot of different materials, and so it's pretty much the customer is designing exactly what they need, correct?
Absolutely. Every customer has a piping spec, and they're trying to stay within that piping spec. And the great thing is the V-cone is built of a spool piece that matches that piping spec exactly. The only difference is we have a cone that's welded in there and a set of taps or more, depending on the customer's application. And then there's also some situations where a customer is trying to retrofit an existing line, an existing meter, and maybe that meter is not manufactured anymore, or it may have not been successful in measurement. So we're able to customize our meters and make them longer or shorter to assist the customer retrofit with very minimal installation costs and time.
And they can do different types of materials, correct, to fit their need or what the application is going to be?
Absolutely. We were basically able to manufacture a V-cone meter from any two metals that could be welded together. We've manufactured as a standard from carbon steel and stainless steel, but we've done plenty of in the past for Hastelloy, duplex, super duplex, some titanium meters, and chromoly meters as well.
Yeah, and I've seen some at the factory that they have, several different ports on them or for transmitters, and so they can pretty much let us know what they need as far as the inputs and outputs, correct?
Absolutely. Whether it's multiple sets of taps or different types of taps, it's a customizable product, so it's really engineered to whatever the operator's needs are. We've done pipe taps, flange taps, MPT couplings, direct mount plates. I mean, you name it, as long as it can be welded on top of the pipe, it's a tap type that we can offer. And of course, extra sets of taps for safety instrumented systems is a specialty of ours too.
Wow, that's great. Well, I don't see any other questions coming in. Again, thanks, Mike, for answering those in a timely manner during the presentation. Sean, do you have any final comments or anything you'd like to tell everybody for being on the line?
I don't have any more comments, but I wanted to thank everyone that's on here for listening and watching the presentation. I mean, we're very happy to deliver this, and as mentioned earlier, should you require a PDF copy of it, we'll be happy to provide you one, and I believe we recorded it, so this presentation should be on YouTube later.
Yeah, so we'll be on there, as well as tomorrow you will get an email saying thank you for joining, and if you'd like to watch it again, because it was a lot of great information, there'll be a link to view it on demand as well.
Great.
Well, one more question came in from Carlos. So Mike, do you want to get that one before we sign off? And again, thanks everyone for joining, taking time out of your day. You'll get a recording of this tomorrow. And please reach out to Sean and make sure you get on our list for any future webinars. regarding RV cone or other applications. And he answered it. So we are good to go. Thanks again, everyone. Thank you, Sean. Thank you, Mike. Anything?
Thanks, everybody.
Okay. Thanks, guys.
All right. Goodbye.
Bye-bye, everybody.